Hello Professor, this is Andy and Jasmine, and I will go over how to run our graph analysis program via the terminal. So once you have your terminal up and running, you go to your development directory or wherever you have our thing called. It is called Graphario, Graphario. So I have the data folder, an extra folder, some images, README and requirements, and a source. I probably should have created an image folder, but that's fine. So just to get things started, we need to create a Venv environment so that you can be able to run Python. So to do that, we just look at my notes. You can also access the notes via the data. So if you want to access the notes, it is right here. So you can access there just to go back and look at the commands. Otherwise, I will look at this. So the first command you need is to create a Venv environment. So if you're already inside your parent folder, just go ahead and do python3 m-venv- whatever you want to name it. So I'm going to name it my container. Go ahead and create a Venv container. All right, it's created. So now you also need to activate it. So to activate it, it's not too hard. Just type in source, the container name / bin. Just activate. So my container. All right, this is all you need to activate the container. All right, so now I have a live container working. Now remember requirements text. This you need to download all the packages using requirements text because that's how Python is. You kind of have to download every single library that is external and not standard. So the command to that is right here too. So if you ever need to go back, remember I have my notes inside data file. So let's see, pip is used for installing. So to install stuff, you just do Python. I think honestly you could just do Python install requirements.txt, but just to you know, I don't know, I guess stay formal, make sure everything works, just follow everything. So it's make sure it's also Python 3 and not Python, but yeah, Python 3 -module pip install -r was requirements requirements.txt. And also make sure that you are in the parent folder. You don't want to be inside another folder where requirements.txt is in. So go ahead and click that. It's going to start downloading all the packages that you need for this program. It's a pretty good amount, so it might take some time. There we go. So to update, yeah, I mean, I guess if you want to, you can update, install, you can do that, but maybe do that before, I don't know, you'll probably already be at the same place where I am. Okay, so now they have all the files installed, and you have the libraries and you have your environments. Then you can get started on running the source code. So let's enter the source code. These are all of my files. So input.py, analysis.py, shortest path, subgraph. Input.py is what we're going to be using as the module for input. So we will do, to run this program, we will do Python 3 input.py and then our member edges.csv file. I already basically made sure that this file, wherever it is located inside this folder, you will find it. So all you need to do is just do member edges.csv. Actually, is that how you spell it? Let's just do this. Make sure I'm spelling this right. Member edges that CS. Yeah, I'm spelling that right. Let me just copy it though. Okay. Python 3 input.py. Remember that it's always input.py. And then member edges.csv, the name of the CSV file that we have in folder. And remember, I already have the CSV file, so unless you want to put it in there, but I already have member edges CSV in the data file. So let's go ahead, and this is going to be the first program output based on only the data file. Okay, let's go ahead and click enter. So it took a little bit of time to build the network X graph, but after that is done, you will be given a progress bar, and we have a total of 3 minutes and 30 seconds to run that. So that's the amount of time you'll have to wait to build the source files. The all pair shortest path CSV and then also the closeness CSV. The reason it took a little bit of time at the beginning is because it needed to download, basically import all of those libraries into there. And it's not only importing the input stuff, but it's also importing the analyzer stuff. So there's a couple of libraries that it's importing. So it's, if you want to go ahead and just wait for that. So as you can see, we still have 2 minutes 20 seconds, and we are 1 minute 27 seconds lapsed. So we just gotta wait a little bit more for that. All right, so we got 2 more minutes left. 2 more minutes. Do not worry, it will work. So yeah, for some more context, right now, member edges.csv is doing all pair shortest paths on all nodes. It is calculating the highest Q score for the most central node. It is also writing the average. It's actually writing the closest centrality score for each node and putting it in the CSV, and it's also calculating the diameter. So now, once that is done, we get the most central node, which is node 3380276. We can highlight it here. And then we get the longest path. This is the longest path based on the maximum of the shortest paths. Right, so I believe this is our source node 233209962, and so the most central node is 3380276, which I'm pretty sure is right here, right? 3380276. Yeah, that's correct. The U score is 0.5, so that's the most central, the highest central closeness neutrality score. The longest path is 23320992184, which is what we see right here. So yeah, 2362, yes, and then 18484. Yep. So that's it. The diameter is 6, meaning the 1, 2, 3, 4, 5, 6. So that's what the diameter stands for. And then part 1 is done. I also printed out a list if you wanted to see the IDs of all the nodes. I didn't have time to put an ID to all of these, but I printed it out here for better understanding. So that is part 1, and that is if you enter member edges.csv. Just for practice, if you enter something else, then basically I raised an exception, and I said something about the file. The file. See this file that you wrote. It's not right. I'm telling you to try again, right? So this is not, a bug. This is I made it like this. Just letting you know. And then also, right, that won't work. So yeah. So member edges.csv. And then now let's move on to flags. But if you need help with that, let's start with -h. So if you do -h, it gives you the args parse. It's a library that I used, and it gives you the options. So -h is help, -g is it gives you a subgraph that starts at node ID and goes to give a depth. If you do -p, it outputs the value of the shortest path from given source node to destination node. So just remember that. If you enter, -g only, it will, tell you that it expects 2 arguments. If you enter -g with only 1 argument, then it's gonna crash. It's not gonna crash, but it's gonna give you an exception. So make sure to give it the right arguments, right? So, all right. So right now, let's look at the second output. So we're going to do -g. And we're going to do a graphical representation of the subgraph that starts at node 1, 2, 3 and goes to depth 5. All right, so just to make things simple, we can do this. Also, I have updated it so it doesn't have to basically calculate the all pair shortest path every time. Once you've done it, you don't have to do it again. You can run the first, input as many times as you want. It'll be faster. So what we can do is we can take this node right here and then basically, do a subgraph based off that node. So member edges -g and then a graphical representation of a subgraph that starts at node 1, 2, 3 and goes to depth 5. So that is the thing, and then we will go to a depth of 2, just to make things fast. All right, just to show. So let's go ahead and click enter. Pretty quick. So I have made sure to highlight the source node. That is our source node right there that we gave it. And we can see that this is at a depth of 2. Pretty good click over here. Oh, also, cool thing about this is it has Barnes physics things, so you can turn off physics, you can turn them on. You'll see what I mean by turning off and turning off physics later, but if you want, you could play around with it. You know, you can move this guy, do some cool tricks with it, right? Just move him around. You can move every single node around. But yeah, and then you can mess with these things too. That's totally up to you. All right, so that's the longest path. That's the shortest. That's the most central node. Actually, no, this is the subgraph based on the depth, and then this is the central node, and that's the longest path. All right, so moving on. Let's say we want a depth of 3 now. So it will take a little bit longer, and I have actually capped it at 1,000 nodes because, you know, I don't want you sitting here all day. If you want to, you know, see a graphical representation of more than 1,000 nodes, all you need to do is go into my subgraph.py, and then in my BFS implementation for the subgraph, get rid of one of the cases that says while, you know, traversing G, and if, you know, the length of the edges is less than 1,000, keep going. So if you want to change it, just, you know, change that. But otherwise, if you go for bigger depths, it'll do it. So this one is of a depth of 3. So this is what we get right now, right? It's pretty cool. We can see all these, you know, bunch of clicks with single connections. You know, this one has some connections, relationships actually. Pretty cool. As you can tell how it moves right now. You can also turn off the physics too if it's bothering you, or if you want to, you know, do some playing around. You want to move it around, see who's who, see if, like, what's going on in the background. See, we can see that this background is like this. You know, we can also move this click more away from this guy to see what's going on, make sure we can see something. So yeah, and then the source node is all the way over here. Here is our source node. This is funny though, because it goes boom. It doesn't start from him. It just goes, you know, boom, 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 and build on that. But that's pretty cool. Pretty cool. All right. So click that graph, and then if you want, you can just turn off the physics again, and then it just keeps moving. Pretty cool. So now we have the subgraph at a depth 3, subgraph at a depth of 2, I believe. You know, the longest path. All right, going back. Okay, now make sure that when you are doing the -g argument, that you're not going to put in some number that's like billions, like mistake it for an ID or something, right? Because that won't work. Now going to P, right? So P is output the value of the shortest path from the source node to a destination node. So what we can do is actually go here. We can give you an example of this, and then the destination node is this guy right here. So I think we should actually get the same value. So from 233 here to 184, whatever, the diameter is 6. So we should get I guess the shortest path from these two, which is the third part. Okay, it's working. Right, the shortest path distance between 23320, which is this one, and 184.840.725 is 6. As we can tell, that matches with this one. So yeah, that is our presentation, and I believe we have met all requirements in terms of program input and output. If you have any questions, feel free to reach out to me. But for now, this is what you get. Thank you.